Hi, in this video we're going to be going over a little bit of an introduction to H3, as it features heavily in most of our notebooks and our aggregation analysis. So what is H3? H3 is an open source hierarchical hexagon indexing system. It's developed by Uber actually, like Uber Eats Uber, and it's used on their massive spatial datasets and helps them optimize the plotting of which directions and like what's the shortest route to things and things like that. It's also responsible for their search pricing, so there's that kind of side of it too, unfortunately. It provides a consistent global tiling across the entire globe at 16 different resolutions. So this lets us see things at a wide scale when we need to and at an incredibly low scale when we need to. The smallest resolution is around 1 meter square hexagons. So the actual technical problem we're solving is that lat-long pairs can be expensive computationally to group and aggregate, and this especially is more complicated when we're looking with complex polygons and other kinds of geometry as well. So for example, in the datasets that we have, there are administrative boundaries which are incredibly, they're good because they're nice high detail shapes, but when you do the computational analysis and try and aggregate, things can be quite slow. And this is annoying for our workflow and all the rest, right? So we want to find a way to speed up the system and have faster technical solutions. So this solution, the H3 tiles that tile the entire Earth, converts basically regions into unique IDs and tags. And this allows us to reduce our lookups from geometry kind of interactions, and they boil down to just a regular old string match. So if this hexagon and this hexagon align, then we know that these things are related. As I alluded to before, it's got this hierarchical resolution. So on the left here, we can see that resolution 1 is quite well suited to kind of continental analysis. These hexagons may even be too large for Australia, but maybe you're looking at Eurasia or something, this might be the resolution you use, but these are quite large, right? Then if you're looking at some kind of state or territory analysis, a smaller region, you might pop down to resolution 4. So the average size has come down considerably for these hexagons. And once again, if you wanted to go even further, so if you're looking at Sydney Harbour, maybe you would use resolution 10. So the average area of these is gone down to the meter squared kind of territory rather than kilometers. And we can see that we can scale up and down the resolution based on the analysis we want to do. So the key technical features for us are we get those incredibly fast joins between spatial information, and this is fantastic, especially when we're working with complex shapes, because they boil down to just simple strings and integers depending on our application. The compactness and representation of complex geometry can also be greatly reduced. So because these indexes have locality sensitive encodings, they tend to become compressed on disk in an extremely highly efficient way, and this reduces the time it takes to download files, for example, and just generally makes datasets more manageable to transmit and load into different systems. And the other key technical feature is interoperability. So there's a C binding, the package for H3 is written in C, and there's a binding in many other languages, so we can work wherever we need to in whichever system and work with the same H3 index and same system under the hood. So in marine data applications, we use it for a couple of things. So first and foremost is our heat mapping and shape tagging. So you can see in the first picture in the middle here, we've got the seabirds dataset, and we've tagged it to the Australian marine regions here. We're using resolution 4, and the average hexagon size is about 1700 kilometers squared. To do this as well, we get the database style aggregation. So we can aggregate millions of points geospatially simply using regular group by statements. This is incredibly powerful and reduces the complexity of the compute and makes all of our queries much, much faster. Additionally, we have this efficient shape tagging. So this central map, again, we've actually reduced this to the Australian marine regions all around Australia, and these are the Commonwealth marine regions. And we could tag all of these points incredibly efficiently using the H3 index mechanism. And finally, you can see that we can aggregate at different scales, and here's an example of that. So we've got on the right the Sydney Harbour, and this is the same mapping, but we've just zoomed in a section here. So in the top right, we've got the entire Sydney Harbour at resolution 12, and when we zoom in, we can see that we get a much clearer picture of what's going on in these regions. In fact, you can see there's the kind of main shipping channels, for example. It looks like there's outbound and inbound traffic to the harbour, and that's clear at this high resolution. There's a number of H3 workflows tools that we use, and they kind of come into our stack and what we use at different times given our use case. So at the start I would say there's the general H3 library for Python, and this is the official Python binding, but it's a little bit simple and it's good for learning, but it doesn't scale well to large data sets. This is where some of the DataFrame API plugins come in. So for polars and pandas there's a H3 plugin. This allows us to have a nice vectorized compute that's extremely efficient, so we can tag and do all our H3 computation incredibly quickly across an entire data set. Finally, for the visualization, we have PyDeck, and there are other systems which have nice integration, but we've found PyDeck works the best. They have a layer system that works directly with H3 hexagons. So the takeaway messages are, for H3, in terms of our NESP datasets, it's highly efficient for our spatial joins. It gives us really nice aggregated heat mapping that's consistent and applicable at different resolutions. And as well, the system is completely interoperable in many different languages and whichever system we might need to use it in.